Okay, so this is a closed loop systems, and here we simply we want to design the K, and that is our ultimate goal. But here, let me use this example to demonstrate how to determine the phase angle, the desired phase margin and gain margin for the certain value of the K. Okay, so here let me say this is the GS. So the characteristic equations equal to simply is GS equal to 0, like this. Okay, and then we want to determine, for example, here. We exercise is this one determine the phase margin of GS. Okay, so basically here we have to try is this how to determine the phase margin and using the graph. So the phase margins is calculated by looking at this definition here. The phase margin is the angle, how to say this one? So let me, based on this graph, I want to calculate this one first. Once I have that angle, then I can measure that one. I can do the calculation. Okay. So for this one, basically here, let me do it. So they calculate it by this and G, okay, and J and omega. Let me follow up that definition and using that one. So it's CG here, okay. So to do this one, and we have this one, basically here we can do the calculation. Let me plug in. So basically that is the angle of the numerator, which is equal to 0 degrees, and minus the angle of the denominators. So that is S and plus S plus 1 plus and S plus 5, and that one when S equal to J omega CG. Okay, so as long as we know the omega CG, then we can do this one very easily. So how to determine right now the issue is what is omega CG. Again, the calculation is once we determine omega CG, you simply put into the calculation for this one. That should be very straightforward, right? Okay, so the issue again. So why we want to know the omega CG? That is where we define omega CG is the frequency at which the magnitude equal to how much? 1, right? Because that intersection with radius 1. So omega CG is determined is such that the magnitude of G, J omega CG, and we know that is equal to 1. The 1 is, why we set up this equal to 1, that is based upon this definition here. Again, graphically, we can look at here, that is intersecting of the body plot with 0 dB. 0 dB, that means this magnitude equal to 1. Be good? Okay, so we set up this one equal to 1, then what is that? So magnitude K, and that is J omega, the magnitude equal to K, and here let us assume the K positive, okay, so for the situation, so this one is equal to 1 J omega, let me say S, and 1 S plus 1 S plus 5, and then S equal to J omega CG. Okay, so basically here is our formulations. So this one, we do this one individually K, and this one basically is omega CG, right? And this one basically the magnitude equal to 1 plus omega CG square, and then the third one is 1. 25 plus omega CG squared. This one equal to 1. Good. I simply individually implement the magnitude of 1, 2, 3, 4, 4 times like this. Okay, so for this one, we're solving for omega CG, and under these situations, basically here, if we rewrite, basically that is okay. So for this case, basically we can solve for omega CG. We can solve for omega CG. For here, let me make up a few scenarios and say when k equal to 10, then if we know the value of the k, then we can solve for then omega CG equal to here is 1.23 radians per second. And for example, here when k equal to 100, then omega CG equal to 3.9 radians per second. Okay. So for this case, right now under these situations, then basically this one we can determine. So when k equal to 10, the angle equal to 164.6 minus degrees. When k equal to 100, this angle will be equal to minus 203.6 degrees. We have such two values here. Okay, and again, once we have omega CG, you simply plug into here. And let me do this one. So what is this one? For this case, so is j omega plus 1. Its angle basically is arctangent omega, right? So for this one, that is j omega plus 5. So that is arctangent omega divided by 5. Right? If you remember, for any complex numbers, so for example, here is a plus jb. So if you look up this one, this is a, this is b. So this is its phase. So that one, this phase is equal to how much? That is arctangent, the imaginary part divided by the real part. So we're simply using this kind of formulation for individual term. This one is very straightforward. That is simply is arctangent, whatever the omega, right? And no, this one is 90 degrees, right? Okay, so right now we have done this one. Then basically here you can see, right now we mark it here. When k equal to 10, that angle is minus 164 degrees. So that means for this case, this plot is something like this. That angle is, we measure 164, so up to here. So basically that plot is something like here, something like this one. So when the magnitude equal to 1, that angle is simply measured is from here to here, 164, right? So by using these informations, so therefore the phase angle, the phase margins will be equal to when k equal to 10. Again, we plug in, or you can map using the graphically. Basically, that is the angles more and the how much angle to the minus 180. So basically, the phase margin equal to 180 plus this one. We plug into these equations, or you simply look at that graphically. So that is equal to 25.4 degrees. I think I made a mistake. This should be 140. And no, my result is correct. This one is 25.6. Okay. So when k equal to 100, again that is 180 plus minus 203.6 degrees. That is equal to minus 23.6 degrees. So this one You good? Okay. So now in the similar situations, we can calculate the gain margin. We determine the gain margins. So you can take a break.